Hello and welcome to another microbiology Bio120 lecture. This lecture is going to be about reduction-oxidation reactions, also known as redox reactions. To remember the various roles in redox reactions, you just have to remember the mnemonic oil rig. Oxidation involves the loss of electrons, and reduction involves the gain of electrons. Microbes take electrons off electron donors like hydrogen sulfide, and they funnel them through electron transport chains in order to produce ATP and NADPH. And then they put those electrons on terminal electron acceptors, like oxygen. The electron donor, such as hydrogen sulfide, loses an electron and so it gets oxidized, while the electron acceptor, like oxygen, gains an electron and so that gets reduced. So the motivation for microbes in doing these redox reactions is that they can gain ATP and NADPH. So let's explore how right now. The electron transport chain is a collection of membrane-embedded proteins and organic molecules. In eukaryotes, ETCs, or electron transport chains, are in the inner mitochondrial membrane, while in prokaryotes they are found in the plasma membrane. The electrons travel through the electron transport chain from higher to lower energy level, as they are taken from electron donors and delivered to the terminal electron acceptor. Along the way, they release energy, and that energy is used to pump protons across a membrane and create a proton gradient, or proton motive force, that is used to power ATP synthase. Here the electrons are coming from the bonds of NADH and FADH2, which are produced during earlier stages of respiration. So if you ever see a redox reaction and you're unsure which compound or which element is the oxidant and which is the reductant, you can just calculate the oxidation states of the elements in each of the compounds in the equation. The oxidant will be reduced. It will gain electrons, and so its oxidation state will become more negative. Conversely, the reductant will get oxidized. It loses electrons, and so its oxidation state becomes more positive. These are the general rules for figuring out the oxidation states of an element in a compound. So each oxygen in the compound adds a -2 to the tally for that compound, while each hydrogen in the compound adds a +1 to the tally for that overall compound. Now the remaining element has to balance those charges out so that the overall charge of the compound either equals 0, or if the compound is an ion, it has to equal the ion. So let's try some examples. The oxidation state of carbon in methane is -4. That's because each hydrogen in the compound adds a +1. To balance the +4 of the 4 hydrogen ions, the oxidation state of carbon must be -4. The oxidation state of nitrogen in ammonium is -3. So again, each hydrogen in the compound adds a +1. But because the overall charge of the compound is +1, you have to get the charge of nitrogen to balance out with the hydrogen ions to be +1 rather than 0. So to balance out the +4 of the hydrogen ions, but keep that +1 charge, the oxidation state of nitrogen must be -3. Finally, the oxidation state of oxygen in molecular oxygen, O2, is 0. That's because the overall charge of that compound is 0. So I'd like you to take a minute, maybe pause the video, and try to calculate the oxidation states for various elements in each of these compounds. Here are the answers. For sugar, the oxidation state of carbon is 0. The oxidation state of nitrogen in nitrate is +5. The oxidation state of iron, when it's ferric iron, is +3. The oxidation state of iron in ferrous oxide is +2. The oxidation state of sulfur in thiosulfate is +2, and the oxidation state of elemental sulfur is 0. Microbes influence the planet via their redox reactions. Through redox reactions, they create biogeochemical cycles for elements such as carbon, nitrogen, sulfur, and more. Remember that energy is unidirectional and travels one way through food chains, while the elements cycle. An important part of the carbon cycle is aerobic respiration, which is displayed here. Try and identify the oxidant and the reductant for this equation. Remember that you can calculate the oxidation states if you're unsure, and that can help you figure out which one gets oxidized and which one gets reduced. So here are the answers. You can see that oxygen is the oxidant. It is getting reduced as it is going from an oxidation state of 0 to an oxidation state of -2 in the water compound. It is gaining electrons. Organic matter is the reductant. It is getting oxidized as the carbon is going from an oxidation state of 0 to +4 in CO2. It is losing electrons. This is a very simplified redox ladder, or sometimes called redox tower, and it just shows you the order that common oxidants, which are found on the top side of the steps in the staircase, will be used according to how much energy they yield by pairing it with a reductant, which is on the bottom side of each step. You can see that oxygen is the top choice. It yields the most energy, and aerobic microbes will outcompete microbes that specialize in other types of oxidants when oxygen is present. Methanogenesis, which uses CO2 as an oxidant, does not yield much free energy, and so it is the last option for microbes in various ecosystems. This is another nice visual of the redox ladder with slightly more information. The oxidants are on the left of the vertical line here, and the reductants are on the right. The line on the far left, or the far right here, has the redox potentials for the various half reactions here, such as converting oxygen to water or turning nitrate to nitrite. Different microbes have the ability to combine different oxidants and reductants. Any oxidant and any reductant can be combined as long as the oxidant appears above the reductant along that vertical line. That means that it's energetically favorable. If the oxidant appears below the reductant, then it is not an energetically favorable reaction, and there's no reason for the microbe to complete that redox reaction, as it will gain no net energy from it. Photosynthesis really sets up the redox ladder. By creating a bunch of oxygen, which is a really strong oxidant, and ample reduced material, organic matter, photosynthesis ensures that the planet is in a constant state of thermodynamic disequilibrium, and other forms of life can benefit from it. And while energy is lost from food webs, elements are not. They are just cycled around and around from oxidized to reduced and back to oxidized states. So you might be wondering how some of these other oxidants form. We know that oxygen is produced via oxygenic photosynthesis, and it's our top choice for oxidants, but there's a lot of other potential oxidants. Nitrate, oxidized manganese, oxidized iron, they can all serve as oxidants. So other oxidants form via other types of autotrophic reactions. Oxygenic photosynthesis is an autotrophic reaction, but there are other chemoautotrophic reactions as well. Some chemoautotrophic reactions, such as nitrification, require oxygen to proceed. However, other chemoautotrophic reactions do not require oxygen to proceed. They just need an oxidant that is above the compound that is being oxidized. So hydrogen sulfide can be oxidized with oxygen, nitrate, oxidized forms of manganese, or oxidized forms of iron. Here is yet another view of the redox tower, and it's showing half reactions and their redox potentials. Half reactions show an oxidized and reduced pair. The E on the y-axis is showing how electronegative or electropositive a half reaction is, and is showing us the redox potential as well. This is similar to the redox tower we just looked at on the previous slide, except with this, there are a few more molecules, and they also flipped it, so it's upside down from what we just looked at. So the reductant has to be on top of the oxidant in this tower in order for it to be energetically favorable. Again, a larger difference, a larger area between your electron acceptor and your electron donor yields more energy, and so it's more energetically favorable. Gibbs free energy is the energy associated with a chemical reaction that can be used to do work. This energy is actually the change in Gibbs free energy, and it can be calculated from delta E there. Spontaneous reactions will be ones with a positive delta E and a negative delta G, meaning energy is yielded. We will practice calculating delta G and delta E using half reactions in class, but take a minute now and try to calculate the delta E and delta G using oxygen to oxidize NADH. Said another way, calculate the delta E and delta G when NADH is donating electrons, and those electrons are funneled through electron transport chains where they are eventually put on oxygen. Note that the Faraday constant can come in multiple units, so be aware of that. So here's the answer to the question that was just posed. You have to calculate delta E first. Reducing oxygen to water has a redox potential of 0.82 volts, and oxidizing NADH to NAD plus has a redox potential of 0.32 volts. Note that I flipped the sign of the NAD plus and NADH half reaction because I was directing it in the opposite way from what it is listed here. So you just have to add these two numbers, or subtract a negative, and see that the delta E for using oxygen to oxidize NADH is 1.14. Now to figure out the change in Gibbs free energy for the reaction. That can be calculated from delta E if you know the Faraday constant, which we do, and the number of moles of electrons that are being transferred across the redox potential for a given delta E. If you look to the right of the redox pair, you will see how many moles of electrons this redox potential is based on. In both cases, it is 2, and so you just insert the number 2 for N, the Faraday constant for F, and the delta E you just calculated. You should wind up with negative 220.02 kilojoules per mole. So this is an energetically favorable reaction because we have a positive delta E and a very negative delta G. Let's look at an experiment now that you may have done in the past that demonstrates the redox ladder. It was invented in the 1880s by Sergei Winogradsky, and the experiment carries his name. To do it, you just take pond mud with water and ample organic matter, which is usually contained in the mud, and you seal it in a glass container. You have to ensure that the column is airtight, and you leave it in the sun for several months. After a few months, you start to see different colors in different layers. These colors are showing you the areas inhabited by various types of microbes that are adapted to different types of oxidants and reductants. And so this is an example of the redox tower. In other words, the Winogradsky column is showing us the various metabolic niches of the microbes in the pond mud. Remember that all microorganisms have a metabolic niche, what carbon, energy, and electron source they use. That is dictated by where on the redox ladder they are adapted to getting electrons and oxidants from. So different organisms are adapted to different oxidants and different reductants. At the surface, you will have oxygenic photosynthesis, and you will also have microorganisms that aerobically oxidize that organic matter. They are aerobic respirers. Below, you will have autotrophic iron oxidizing bacteria and heterotrophic iron reducing bacteria. They are heterotrophs because they're using organic carbon. Below that, you will have various types of anoxygenic photosynthesis that produce organic matter and a more oxidized form of sulfur. Because there are oxidized forms of sulfur being produced, you will also have heterotrophic microbes that use sulfur as an oxidant, heterotrophic sulfate reduction. The reactions and where they are depend on the elements found in the mud, and the order will also depend on the redox ladder. You may get methanogenesis if you have a zone with no oxidized sulfur compounds, but if there's oxidized sulfur present, then CO2 will not be a preferable oxidant because sulfate yields more free energy, and those bacteria, or archaea, will outcompete the methanogens. That concludes this lecture.